Okay, hello everybody, and today we'll be talking about this problem, which was on the International Mathematical Olympiad, the shortlist uh, of 2020. So it asks us how many permutations are given by a1, a2, etc. of the integers from 1 up to n. And so we've shuffled them around and relabeled them a1 up to an. And now we want to know how many permutations satisfy this relation. But we multiply each element by its index. And well, of course, there's always going to be one permutation that does satisfy this, namely if you just let ai be pi. But there will be some more. And we want to know for each n how many of these permutations exists. And to start, we're going to look where in this permutation where's n going to be. Well, of course, an can be n, so an can be equal to n. That's going to be case 1. That's definitely the case, but and we're interested if n can get in some other place. So what if an minus 1 were equal to n? This is case 1, this is going to be case 2. Well, then by this relation we know n times an is going to be bigger than n minus 1 times an minus 1, which is n. So this immediately gives us, when dividing by n, that an is bigger than or equal to n minus 1. And well, we've already used n, so in fact an must be equal to n minus 1. So that's interesting. We'll then look at the third case. What if ak will be equal to 1, in this case 3, but here k will be less than or equal to n minus 2. I'm going to use all of them. Well then, we start by picking a random I which lies in between k and n. So 4 for all I with this property. And we know that k times n is equal to k times ak, because we know ak is n, that's what we supposed. And well, this is going to be less than or equal to I times ai, just by these relations that we were given in the beginning. And I is less than n, so this is going to be less than n times ai. And well, of course, from this and this part, we see that when we divide by n, ai is going to be bigger than or equal to k plus 1. Well, now we tackled all I between there, but we don't know what's happening at n. So let's have a look at n times an. Well, this is definitely going to be bigger by these relations to n plus 1 times n minus 1, n minus 1. And this is definitely going to be bigger than or equal to n minus 1 times k plus 1. Because we know an minus 1 is of the form ai, which is bigger than or equal to k plus 1. So we can take that, and we can multiply this out. It will be nk plus n minus 1 minus k. And well, we know this last part, because k is going to be less than or equal to n minus 2. This is strictly positive, so n times k is bigger than this. So shoot from this part and this part together with this symbol in the middle, we can also conclude that an is going to be bigger than or equal to k plus 1. So we now know that for all these i's and for an, those are all bigger than k plus 1. So we now have a list starting at ak plus 1, ak plus 2, etc. all up to an. We know all of these elements are bigger than k plus 1. But how many elements are there? Well, in total we here have n minus k plus 1 elements. And how many are there left bigger than n? Those are minus k. So those can never fit, and those are more than this. So we just don't have enough choice for all of these, and one of them can't be bigger than or equal to k plus 1. So we reach a contradiction. And therefore we now know that there are only two cases, namely an equals n or an minus 1 equals n, together with the fact that an is n minus 1. Now it looks like we haven't gotten much at this point. Maybe we want to know all permutations, and we just gotten two facts about just where n lives. But it turns out we're quite far, because if we call the number of permutations that satisfy the equation p sub n, we know you can just calculate p1 will be equal to 1. There's only, if you get just one element and the set, the single element 1, you can only permute it in one way. And obviously they satisfy the equations, because then there are no equations, so that works. And for p2, well, you can have 2 is less than or equal to 2 times 1, and you can have the 1 is less than or equal to 2 times 2, so just both permutations satisfy, so p2 is equal to 2. And now by these two relations, we know either one of them is true. So in the first case, and we get that n is just in place, and we just have a permutation satisfying all the equations we needed for n minus 1 variables, and you could check that this extra condition n will always be satisfied, and so you just got pn minus 1. For this case, you have 2 already filled in, and so you've just got a permutation satisfying the equations for n minus 2, and you can check that the extra conditions are always satisfied. So we get this equation, and this looks kind of familiar. This is Fibonacci, and together with these two facts we found up here, we see that p sub n will be equal to Fibonacci number of n plus 1, and there we already got our answer. Isn't that neat? And then we solved a International Mathematical Olympiad. It was only shortlisted. And it was, I guess, combinatorics 1, but we've already solved it in under 10 minutes. So that's how easy it can be. Of course, when you know the solution. I've tried this thing myself. I used a way harder proof when I tried to solve this problem. It was way longer. But, well, this is how easy such a thing can be.